Very good morning to all. In unit number 4, that is inverter, we are going to see today various PWM technique. PWM is pulse width modulation technique. Okay. So when you see in last class we have seen single phase and three phase inverter. So single phase inverter will get the input DC and you will get a single phase AC supply, which means a phase and neutral. In a three phase inverter, you input a single phase DC we will give. In DC we cannot call it as phase and all, it is only positive and negative, and the output of three phase inverter is three phase supply, where you can connect it both in star and delta, which means when you connect it in star you will get phase and a neutral. So phase to neutral you can get it, so it will be around 230. Okay. When you go for delta, you have phase to phase connection, which is around 440 volts. Okay, so that is the two difference. Now how we are going to get the sine waveform? See, our intention is what you get it from EB is a sine waveform. Okay, whereas when you try to do it by inverter method, we get square. Last class I have shown you only a square waveform. So the square and sine both are not same. For appliances, like if you have your ceiling fan, where you should give a pure sine so that it will rotate very smoothly. Rather, if you give a square waveform, it will jog. Jog means it will jump from one position to one position. So this may leads to damages of your bearing and all. So that is why the reason we go for nowadays Sign PWM inverter. When you go and buy a inverter at a shop, you ask them for sine wave inverter. So we will not go for square wave. Again I repeat, the square wave inverters will try to damage your bearings. Bearings is, once the bearing is problem has come, then sound will come from your ceiling fan. Okay, now today from that square wave, how we are going to get sine? We cannot get pure sine as what EB is giving, but we will try to reach pure sine with some reduced harmonics. If it is square, then the harmonics will be more. Okay, now so by starting pulse width modulation, the most efficient method for inverter output voltage, the constant input voltage is applied the input of the inverter, and the output voltage is controlled by switching semiconductor device of inverter in this method. So there are so many methods for getting your AC output from the DC input. So whatever way you go, you should know what is the advantage. There are no necessary for extra components to control the output voltage of an inverter when you go for PWM, as the lower order harmonics reduce where higher order harmonics are introduced. Only the lower order harmonics filtering is difficult. So when lower order is not there, then for us there is no issue. Higher order harmonics can be easily filtered with the help of a simple filter circuit. So now let us go to single pulse width modulation. This is what we have seen in last class. Single pulse is, see, for an inverter circuit, let us assume we are going with a single phase inverter circuit. In single phase inverter circuit, there were 4 switches, 2 switches for positive half cycle and 2 switches for negative half cycle generation. But the input is DC, output you need AC. So for converting this DC to AC, I want to change the direction of current. So during particular duration, it has to be in positive direction, and then you have to go to negative direction. That's all. Unidirectional has become bidirectional or alternating in fashion. That is why we call it as AC. Okay. So now this T on of the switch T1 and T2, either you can turn on and turn off. That is called as single pulse width modulation. Okay, the gate signal is generated by comparing VR amplitude reference signal and VC amplitude control signal. I will show you. So to generate a pulse, okay, to generate a pulse, I need a person called reference signal, I need a person called carrier signal. Okay, so now for an induction motor, single phase induction motor, Speed of the induction motor is controlled by amplitude of your voltage, input voltage. So amplitude of your input voltage. So if you reduce your amplitude, your speed will come down. When you increase your amplitude, your speed will increase. So what I am going to do is, I am taking a V reference. The name reference itself comes from there. What is the voltage which I require? So what is the voltage I which require is specified by the reference. So this signal is called as a reference signal. Okay, now I want a carrier. With the help of, see, when you want to compare, let us assume if somebody is asking, they have given a chalk piece to you and they ask what is the height of this chalk piece, whether it is a small chalk piece or a big chalk piece. If they ask, the only thing what you have to ask them is, give me the reference with what you want to say whether the chalk piece is small. When you compare a 5 centimeter chalk piece with a 10 centimeter chalk piece, then you can say chalk piece is small. When you compare the same 5 centimeter chalk piece with a 2.5 centimeter chalk piece, then the same chalk piece will become large. Okay, so if you want to do, then you should want a person called carrier or reference with carrier. So you can see here, if I move this line either below or above, see, if this VR reference signal is brought down, voltage will reduce. If I increase, the voltage will increase, both in width as well as in height. Both in width as well as height. You can see here, now if I move this up, the area of this will increase. When the gate increases, your voltage will also increase. So you can see here, what can be the maximum voltage which I can generate is turning on at 0 itself and turning off at pi. In that case, I will get maximum voltage. Then if I reduce the reference, automatically my width as well as amplitude of my output voltage reduces. Thereby net voltage or RMS voltage reduces. Thereby when you connect any motor to this single phase inverter, the speed will come down. I think you are able to understand, but there is only one pulse per cycle. See, you can see, for positive half cycle we call it from 0 to pi, for the negative half cycle we call it from pi to 2 pi. So for the entire duration of 0 to pi, there is only one single pulse. So that is why it is called as single pulse with modulation. Only single pulse for the entire time period. Okay, then again this will repeat, but for a single cycle I am saying, for a positive half cycle starts from 0 to pi. So between this 0 to pi I have only one pulse. So it is called as single pulse with modulation technique. Okay. So the frequency of the output voltage depends upon the frequency of the reference signal. The amplitude M is a ratio of reference signal and the carrier signal. This is what I have shown here. So this is amplitude. Amplitude is decided by VR by VC. The analysis of waveform shows the Fourier series. The output voltage become maximum when the width pulse become pi. This is what I have told. So this reference, if this is brought here, then you will have maximum. When the reference is brought to pi, you will get maximum. The RMS voltage is nothing but VDC into root of D by pi. And the maximum value of nth harmonic, this is from Fourier series. You might have studied in max Fourier series. So if you write Fourier series, the harmonic is given by VLN is equal to 4 VDC divided by n pi. Here you have pi, it becomes n pi into the theta terms variation. Theta times is nothing but sine of n d by 2. Okay, n is your harmonic level. If you want to find what is third harmonic, then VNL, here you have to put 3. So 4 by 3 VDC pi into sine of 3d by 2. Okay, that will become the harmonic value of third harmonic in your signal. From the equation 1 and 3, I can say VLN by VL is equal to sine of nd by 2 by n. Okay, so this is with respect to single pulse PWM. So now in this equation I have substituted value of n. So if value of n is equal to 1, that is called fundamental, that is sine of d by 2. Then this is for third harmonic, fifth harmonic and seventh harmonic. The value of fundamental component become equal to 0.14, the third, fifth and seventh harmonics become equal. this will conclude that higher harmonics present when the output voltage is low. When your voltage is less, your higher harmonics will be there. When the voltage increases, your lower harmonics also come into picture. So this is a graphical representation where n is equal to 1, this is not harmonic, this is fundamental. Fundamental is what we need. Others are harmonic. So waveform of third harmonic will be like this. Then waveform of fifth harmonics will be like this. See, in a single cycle itself, the harmonic is repeating, and this is seventh harmonic. And further, if you go, the amplitude of the harmonics will come down. The higher harmonics will have lower amplitude, and the lower harmonics will have maximum amplitude. Okay. Now let us move on to multiple pulse with modulation. So between 0 to pi itself, now I am going to generate more number of pulses, that is turning on and off, so that I can even come down in my harmonics. There are more than one pulse per half cycle is in multiple pulse with modulation technique. These gate pulse are used to control output voltage of the inverter as well as reduce harmonics. This is what is conclusion. For a single pulse, from single pulse to multiple pulse, what happens is, it is not there, it is only controlling the output voltage. Single pulse with modulation technique as only controlling your output voltage, whereas when multiple pulse with modulation come into picture, the gate pulse are used to control the output voltage of the inverter as well as reduce the harmonic. The magnitude and the width of the pulse are equal in this method, which means I am repeatedly generating pulses, but the width of the pulse remains constant. Width is not been changed. The reference signal and the high frequency carrier signal are compared. Here you can see, for comparing, I have taken only, see here I have taken only one. For the 0 to pi, your carrier signal is also only at lower frequency, 50 Hz frequency. But if I want multiple PWM, this 50 Hz carrier frequency has to be increased. Okay. So you can see here. Now between 0 to pi itself, I have 1, 2, 3 times repeating carrier signal, which means the carrier frequency is very high. This is called frequency. From this magnitude to this magnitude, we call it as time period. 1 by of time period will tell us about the frequency. See, my output, I want to get only 50 Hz. So my output will be, see here, you are getting positive half cycle from 0 to pi, then from pi to 2 pi I am getting negative half cycle. So output frequency is 50, whereas the carrier frequency is higher. Okay, you can even go for this 3, you can increase to 4, 5, 6, 7. So thereby you will get more number of pulses here. So more number of pulses means you are reducing the harmonic to the greater extent. Okay, so this diagram you have to draw for multiple pulse with modulation technique. Okay, so now carrier frequency we call it as FC, reference frequency we call it as FR in Hertz. Okay, 1 by FC is equal to pi by 3. Here I have taken 3 times. Okay, so TC is equal to pi by 3. Similarly, 1 by 2 pi R is equal to 1 by pi. This I should not change, students, because this is my output. 1 by pi is nothing but my output. Okay, so TR is equal to pi by 2. So number of pulses in half cycle we call it as NP. It is equal to length cycle reference or signal length of one cycle in triangle wave. So I told no, you can increase the number of pulse also. It is not that I have shown in graph only 3, you can go for n numbers. So if you are going for very high frequency like 20 kHz, 25 kHz, then you itself can decide how many times that will repeat. Okay, so the RMS voltage is equal to VDC square root of NP into D divided by pi. N is nothing but number of times the pulse is going to occur. As the number of pulse increases in the each half cycle, the lower order harmonic reduces but higher order harmonic increases. Okay, but that is not. So once this lower order harmonics reduces, then automatically for us the complication is reduced, because in lower order harmonics only filtration is difficult. Higher order harmonics you can easily filter. Okay, so multiple pulse width compared to single pulse, you have reduced the lower order harmonics. Again, this you have to remember, student, from comparing with the single pulse to multiple pulse. In multiple pulse, the lower order harmonics magnitude is reduced. Okay, it is noted that switching losses of the semiconductor device increases as there are more number of pulse per cycle. Obviously, you are turning and turning off your semiconductor at faster rate and turning and turning off more number of times. So switching loss will increase, but don't worry, now we have latest semiconductor devices, thereby losses can be reduced. This modulation technique is also called as symmetrical modulation control. Okay, even in university question paper they can ask you to explain symmetrical modulation, then you have to write about multiple pulse. Now comes your sine pulse width modulation. So what the change I am going to do is, you are taken your carrier as what I have taken as triangle. So rather taking as a triangle, with comparing with the reference as a DC voltage, take this carrier as triangle but compare with the sine waveform itself. So initially pulse width will be less, but pulse width gradually increases and reduces, so that now you get an output as if like a sine, but pure sine we will not get. Okay, the reference signal is taken as sine waveform, whereas the carrier signal is taken as triangular waveform. The width of the pulse in Sign PWM is not equal, where in multiple pulse you have seen that the width of the pulse is constant. You can see here the width remains constant, but in Sign PWM the width is not constant. The amplitude of sine waveform is also not constant. The width of the gate pulse is determined the interest of point of sinusoidal waveform and the triangular waveform. Now I will show you the waveform. See, you can see here, their reference I have taken as a single DC value, whereas here I have reference I have taken as a sine signal. So what happens is, here the width will be less, here width will increase, and again width will reduce. So when you see here, it is like a sine. How sine will be, sine magnitude will continuously vary. Again, if I increase more number of or increase the frequency of the carrier, then I will get more pulses, and the pulse will be like gradually the pulse width will increase, and then it reaches maximum, then again gradually it will reduce. So that's how you are able to generate Sign PWM. Thereby, when you by Sign PWM, the lower order harmonics are further reduced. Okay, the analysis harmonic is done by in Sign PWM control is below, where the value of modulation index is less than 1, the maximum harmonic number in the output voltage. The NP is number of pulse per cycle. As the number of pulse per cycle increases, the higher order harmonic also increases. Let NP is equal to 4, it will have 7th harmonic and 9th harmonic, but the odd harmonics are easily filtered. So whenever you have higher order harmonics, filtering is easy. This is what I am repeating from the first. In terms of harmonics, only lower order harmonics elimination is difficult, higher order elimination is easy. When lower order harmonics is there, lower order harmonics can be eliminated by going for this modified PWM techniques. Okay, so that is called Sign PWM. Okay, now even from Sign PWM we are able to go for modified Sign PWM technique. This modified Sign PWM technique, we will slightly change what we have done for Sign PWM. So gradually we will increase, and center portion width will be more. That is called modified Sign PWM. The carrier wave is applied for the first and the last 60-degree interval per every cycle. So that sine wave I am going to give only for 0 to 60 degree as well as last 60 degree. The in between values I am not going to give as a sine, rather I will give as a square. So that is called as modified Sign PWM technique. You can see here, from 0 to 60 degree only I have applied sine. Again for the last 60 degree I have applied. So in between I have not applied sine and I am getting maximum width. So by this the lower order harmonics can be totally eliminated from the system. Only higher order harmonics will be there, and that higher order harmonics we will easily filter. And the last topic for today's discussion is space vector modulation. So this is some latest modulation technique where this itself is a separate unit, but just for your sake I will explain what is space vector modulation. It is an algorithm for the control of pulse width modulation. It is used for creating of alternating current waveform, most commonly to drive a three-phase AC powered motor. So this space vector PWM is not applied for single phase, it is only applied for three-phase. And also when you want to give it for motor load, we go for space vector PWM. The variation of space vector modulation that results in different quality and computational requirement. One active area of development in the reduction of total harmonic distortion created by rapid switching inherent to this algorithm. Okay, so we will see. So you have totally, we will separate it into 8 sectors starting from sector 0 to sector 7, which means the entire 360 degree. You can see at the entire 360 degree of your sine. See, this is even like this you can also represent or represent by a normal method. So see here, I will show you. See, it is 0, this is 180, this is 360. So I can even draw it like a 0 to 360, and this 0 to 360, and in this 0 to 360 what they in space vector they are doing is, first they will split it into 6 parts, 1, 2, 3, 4, 5, 6, and each part they call it as a sector, and in that sector they decide the value of firing pulse. So first what they will do is, they will find that they will take one reference 3-phase supply from the EB, they will from that reference, now they will identify they are standing at what position of that 3-phase sine. See, sine will be time varying person. So then they will find the sector, then from that particular sector they will start firing. So when you see here, this is how the pulse width is: maximum width, then reduced pulse width, then reduced pulse width, and these are the 3 for top 3 thyristor. For bottom 3 thyristor, just they will give opposite of this. For example, thyristor 1, 2, 3, 4, 5, 6. So for one, previous leg is third leg bottom. So for third leg bottom, you will have pulse only in this portion as well as in this portion alone. Then when you fire the second leg person, the first leg first leg bottom switch will be fired only for this part alone. So it is nothing but complement. So they generate 3 pulse, and the remaining 3 pulse is just complicated of complement of this particular pulse. This pulse, if you take complement, that pulse will have only at this portion and this portion, and this for this complicate is this 2 portion, and for this complement is this 3 portion. So like that we will try to generate the pulse and try to give it. So thereby what happens is the harmonics is reduced to the greater extent. So with this we will stop today.